long for you to remember where we were at the end of last class. It was only 3 hours ago, and I'm sure you've busily been reviewing your notes ever since, and that's all that you've been. But where we left off is we were considering a CSTR that had an immobilized enzyme system, in it. And we had some flow rate in with S naught, some flow rate out with same flow rate out with SB. Remember, SB is the concentration of your substrate in the reactor. And we also recognize that there is a mass transfer limitation next to the immobilized enzyme. So to capture the mass transfer limitation, we constructed JS equals KL SB. Okay. Sorry, I'm just going to leave it. Is it going to really bother people if I leave the square brackets off that mean concentration?
No.
Okay. No, you guys are okay with that? Okay, thank you. Minus SS equals EM prime SS over KM plus SS. So just reminding you, EM prime means that it's per unit area. SS is the substrate concentration at the surface. And of course then SB is the substrate concentration in the bulk. Okay. Because it was a CSTR, we also came up with it also equaled F times S naught minus SB over AT. Now, we basically have, we got one more equation, but we got one more unknown with the S naught when we threw in the balance around the CSTR. And we said, okay, now we need to, what we really want to say, for example, one thing we might really want to do is figure out what SB is. Okay. But it's not easy, we don't know what SS is. We'll probably know maybe what S naught is. We'll probably know what our area is, we'll know what our flow rate is, we'll know what our mass transfer coefficient is. Okay, so let's consider, I'm not going to solve it, I'm going to leave this as one for you. Let's consider one where we have KL 2 times 10 to the minus 3 meters per minute. F equals 2 liters per minute. S naught equals 15 milligrams per liter. AT equals 1 meter squared. Km equals 2.5 milligrams per liter. And BM prime equals 15 milligrams substrate per meter squared minute. So now we've got a really fairly complicated set of equations, and we have all of those data, but if you just plug it in, are you going to, like, is there an easy way to figure out what your substrate coming out is? You've now got substrate coming out in a couple of different places. If you do that balance, it's going to be pretty ugly. If you're smart and set it up well, you could try and use solver, but it's still ugly. You still have to think about how to set it up well. You could try trial and error. In some ways, that's actually the easiest if you have Excel in front of you. So we'll go through how you could do trial and error. I'm not actually going to solve this. I'm just giving that to you as an example, and you can solve it on your own, but we'll go through the steps that you have to take to solve it. Okay?
Did we get asked on the midterm to solve this?
You would never get asked to, so this essentially, the methods that I'm going to present you are all iterative. So So I would never ask you to run through an entire set of iterations until it converges, because that's a waste of everybody's time. I would ask you to run through one set of iterations and then say, next, we would substitute this into there and do the same procedure again until it converges.
Okay.
It's a waste of midterm time to do that. However, the most alert amongst you may have noticed, I bet nobody has because I just did it, I just posted assignment number 2, and it's quite short, but it gives you practice doing these problems. And what I posted, you can decide if you disagree, and I'm willing to listen to alternatives, but what I posted is, as a suggestion, was have it due at the end of the midterm, so that you have it, you can practice on it, but you'll have it actually in your hands for the midterm, the open book midterm, and then hand it in at the same time as the midterm. Is that okay?
If we have it due before, can we have solutions for the midterm?
That's really awkward to do, because I'm just not gonna print out. My solutions, honestly, are pretty messy.
No, but just like scan it and post it to Avid, scan the solution and post it to Avid, and we'll look through them.
Yeah, but most people are gonna want to have printouts for the midterm, I would imagine.
Yeah, myself included, that's what we've done in the past, like for 3 can't stuff, keep printout solutions.
Yeah, it's just because it's Monday that we get back from reading week, I think that's
Alright, yeah, we're.
pretty short. Your timing is pretty tight to actually hand it in and then have solutions posted and printed off
Right.
immediately after. But what I am willing to do, we have one class before the midterm. So if people have any questions about the assignment, we can use that class to talk about the assignment, among other things, but yes, yeah,
How much more content do we have to cover before the midterm?
very little.
Okay, so we should have some time at least on Wednesday just for question and answer sort of thing?
Yep.
Also, assignment 1, solutions will be posted.
Oh, yes, I just haven't done it yet.
Yeah, as long as it's before the midterm.
Yes, it'll be posted before reading week,
Okay, thanks.
part 1. Are we calling it reading week?
Fall break.
Fall break.
I think it's a mental health break, is a technical.
I got an email about that.
Yeah.
The survey?
It's probably gonna see if it actually has an effect on your mental
Yeah,
health.
does this break reduce stress?
Yeah.
No,
I
it makes it
heard-
worse.
I heard it helped it trying to go up with suicide, it's trying.
That's positive.
It's
Although the
friend.
fact that they have to say all that suicide is actually really concerning.
I think the problem is that it's trend, other schools that have no trend.
And I get to.
Okay. So doing it iteratively, the best way to get back on track, the best way to do it is, let's go through step 1. Take a guess at what your substrate concentration would be on the surface. So there are always limits for what your substrate concentration is likely to be at the surface. It'll never be greater than the entering substrate concentration, right? And it'll usually be higher than 0. So guessing somewhere a third of the way between 0 and your substrate concentration entering is probably a pretty reasonable guess, at first guess. You can start it halfway, you can start it a quarter of the way, somewhere around there is probably a pretty good first guess. Okay, so if we guess SS, then, so let me just number the equations. We'll call this, I'll just say equals Vm prime SS over Km plus SS. We'll call that equation 1. I know it's backwards, we'll call that equation 2. Because I wrote it upside down in my notes, sorry. Okay, so step 2. Calculate the flux. from this. So I've rearranged equation 1. So equation 1 rearranged. So we've calculated the flux based on SS, and now we're rearranging this. So equals JM.
Yeah, what's the difference between JS and JM?
Sorry, it should be JS. I don't know why I put in JM. No difference at all. It's just that I'm tired.
JM on in.
Okay. And there's another JM. I don't know why. Okay, so flex to the sphere. Or flex to the surface, sorry. Okay, so we've got, I rearranged this so that it isolated the bulk substrate concentration in terms of the flux that we already calculated, the area, flow rate, and the initial substrate concentration. That looks pretty straightforward. People follow that rearrangement pretty well, I hope. Okay, and then step 4, calculate SS new equals S E minus JS over JCal. Okay, so we still use the same JS that we calculated up here, but now we rearrange this part using the calculated SP that we calculated from this equation. We rearranged that so that we calculate a new SS, so surface substrate concentration, from that equation. And then iterate till convergence.
So you just keep doing it until SS equals SS new?
Exactly. So then, obviously, you calculate your new SS, you substitute it in, or we start again at step 1, but we use the new SS. You calculate a new flux. Based on the new flux, you calculate a new surface concentration. Based on the new surface concentration, you recalculate a new surface concentration, and you keep going through all of those steps until the convergence. Okay. So the basic balances are pretty straightforward. We're balancing the rate with the diffusion rate, the reaction rate with the diffusion rate, and we already saw this balance before, the reaction rate balanced with the mass flow rate through the reactor. Except in this case, now we've got this. Actually, that original area term actually would be multiplied there because we've got a reaction rate that's per unit area. Okay.
Area or volume?
Because that's prime, it's per unit area.
Oh, right, remember that, yeah. Double prime would be the volume, right?
So no prime is per volume of fluid or solution, and double prime is per volume of particles.
What use is that? Are we going to get into that later?
Yes, we are. Actually, we're about to get into it right now.
Okay.
Always one step ahead,
Oh,
Carl. It's good, it's good.
It's everyone's time to do.
It's good. Means we're all getting you to think where you're supposed to be going. Okay. So any questions about that basic procedure? So I gave you numbers primarily because I want you to look at the numbers and be able to practice for yourselves going through that procedure and confirm for yourselves that it works and this is a good way of doing it. I'm not going to give you the numbers because it's tedious to talk you through all of the numbers in class. I don't think it's a good use of the class time. But the steps are very helpful. And everyone, that makes sense, right?
We've done the same thing with 3D, so.
Yeah. Yeah, I think in lots of other classes you've done the iterate to convergence. It's like good chemical engineering procedure. Okay, so now, that's all well and good if you've got enzymes immobilized on an impermeable surface. But I told you the other way that enzymes are often immobilized is in a sphere. Okay, so we've got enzymes evenly distributed throughout a sphere. Now, there are lots of ways where they're not evenly distributed throughout the sphere. They have a different distribution at the surface and at the center. We're going to imagine that they're evenly distributed throughout the sphere in order to allow us to do our calculations. I'm not going to go through the full math derivation, but I will tell you how the math derivation is done. You see what I'm saying? Like what they do in order to do it. I'm just not going to take you through the math of it. So where it comes from is before what we were saying is the amount that reacts on the surface has to equal the amount that diffuses into the surface. But now what we've got is an amount reacting in the particle that has to equal the total amount that's diffused into the particle. So we have some diffusing in here, some diffusing in there, some diffusing in there, some diffusing in there. So essentially what you do is it's called a shell balance. So there's your total particle diameter R, and then we've got some little diameter, and then this part we call dr. Okay, so essentially what you say is the amount that diffuses into the outside shell equals the amount that diffuses out of the inside shell. So one minus the other is the total amount that's diffused through that shell. Does that make sense to people? And then essentially what you do is you integrate it over the sphere. I'm not going to do that. It is in your book. If you're really interested in the math, you can go through it. I'm going to go through a little bit of the derivation. What you end up with is your total diffusion in equals dE, that's your diffusion coefficient, times squared S over dR squared plus 2 over R ds over dr, and that equals total reaction equals Bm double prime S over Km plus S. Okay, now, lots of things influence the diffusion coefficient in the matrix. So, it depends on porosity, on tortuosity, if the pore sizes are near molecular weights. So if the pore sizes are near the actual molecular weight of the substance, then it changes that a little bit as well. Whether the pores are interconnected changes your diffusion coefficient. There are correlations that are available if you know things like how much of what your tortuosity is, what your porosity is, all of that, you can figure out diffusion coefficient. We're not doing that in this course. So again, I will just give you diffusion coefficients. I will not expect you to figure out diffusion coefficients because it's not a mass transfer course. Okay, so now we've got something that still doesn't look very useful. It's the shell balance, so we still need to, we're still actually ultimately going to need to integrate that so that it covers the entirety of the sphere. Okay. So the first thing we're going to do is define, well, I'm going to actually ask you a couple of fundamental questions first. Now the fundamental questions are, when it's in suspended in a sphere, are your VM and KM going to be the same as if they're in solution? So you know what we talked about how to do the reactor, the experiment, so that you can figure out what VM and KM were early on in solution. You use your line Weaver Burke plots and initial rate studies. How about in a sphere?
No, because the things in the middle of the sphere aren't going to be as active as things on the outside. Well, they could be, but I think it takes longer, basically.
So we're going to figure out how to deal with the it takes longer part. But the VMs and CAMs end up being a little bit different. So what you end up having to do is similar reactions, but you have to have things incredibly well stirred so that you get rid of, you don't have essentially the film around it, you don't have to worry about that. So we already talked about how there's a static film that's a diffusion barrier to get to a surface even of a sphere. You have to mix it so well that that static diffusion barrier is minimal. And then you can do a good bet at estimating what your PM and VM are. Again, I'm going to tell you what they are, but in the real world, that you're going to have to do experiments probably. Okay, so it's not really convenient to deal with the expression in the way that it is. So what the book does is it takes you through using dimensionless constants. So we've seen that a lot in fluids and so on. So we'll define a few. S bar is S over SS. So this is not now the bulk substrate concentration, it's the substrate concentration inside the particle. Okay, and that is the substrate concentration at the surface of the particle. So that's telling you S bar is going to be less between 0 and 1. Okay, R bar is somewhere in the particle divided by the total radius of the particle. Okay. And beta is Km divided by SS.
What's beta actually represent?
So that's a really good question Cece just asked. And we're gonna, I was gonna talk about it in a minute, but I'll talk about it now. If you remember, so there we've got substrate concentration, there we've got rate. If you remember, here's Vmax. At half of Vmax, that's what Km was. Okay. So beta is giving you information sort of about where you are in this curve. So if you have, would beta be really big or really small here, where a substrate concentration is really high?
It would be small, the denominator is big.
So where beta approaches 0, then you're getting 0 order reaction. So because we're way past the Km, that means the speed of the reaction is basically not dependent anymore on the substrate concentration. Or in other words, fast reaction, probably diffusion limited. Okay. And then where beta down here, you've got you get really, really low substrate concentrations. Where's my notes?
So at Vmax over 2, the beta would be 1, right?
Sorry, at
Vmax over 2, so half Vmax?
half Vmax, Km would equal S, so
Yeah.
beta would be 1, yes, absolutely right. So right, where it's really small, then it's a first order, it approaches a first order reaction, and it's more likely to be reaction limited. So the beta is telling you something about what the situation is as far as the enzyme itself. Is it actually likely to be diffusion limited, or is it likely to be reaction limited?
Okay, thanks.
Yeah, so that was a good question. Okay. So once we use those dimensionless constants and rearrange that, we get that's the same shell balance that we had before, but in dimensionless terms. Now we're going to define something called the field modulus. Here, what does that actually mean? So same thing as CCS, but about beta. It's basically the first order reaction rate divided by the diffusion mass diffusion rate. So again, it's now incorporating the balance between, is there more reaction or is there more diffusion?
So it's like the dA, but for microencapsulation?
Right. Right, it's a little bit different, but yeah, that's the
idea
the concept is the same. Okay, so what that allows us to do, I can do the math, but I think that's maybe not worth doing it. What that allows us then to do is say d squared s r squared plus 2 over r plus r equals field modulus squared S over 1 plus S over beta. Okay. So that's all very well and good. We still aren't at anything that's actually useful to use. So what they do now is say, okay, what are the actual boundary conditions we can say? So here at the surface, at R equals R, what's our substrate concentration equal to? SX. Okay. And right in the middle, r equals 0, the change in substrate concentration with radius is 0. So using those boundary conditions, so in other words, you can rephrase that as S equals 1 at R equals 1 and ds by dr equals 0 at R equals 0. Okay, and integrating the whole thing over the sphere with those boundary conditions, now we end up with something pretty ugly. And what it ends up being in the useful way is, this is rate per volume of spheres equals an effectiveness factor, B double prime SS over KM plus SS. So what's that effectiveness factor? Okay. So the effectiveness factor really is telling you, so it's 1 if not diffusion limited. So in other words, it's like the ratio of activity in spheres divided by activity in solution. So if it's behaving just as it would in solution and diffusion is not a big deal, this stuff can just diffuse right in and then react, and the diffusion's not in the way, you're gonna have an effectiveness factor of 1, and you're just going to look like your reaction rate is pretty normal, right? But if it's not, if it's less than 1, then there's some limitation due to the spheres diffusing into the spheres themselves. Okay, so that's a lot of skipping steps and showing you the most fundamental part of the math, but the important part is this part. That's the part you're going to use.
So the effectiveness is less than 1, that means that there's some hindrance of diffusion into the sphere?
Right, exactly. Exactly. The other parts, you still need to know what the field modulus is and what beta is, because in your, to actually figure out what your effectiveness factor is, you need to use a graph that's in your textbook. And to use the graph that's in your textbook, you need to do some of those calculations. So I will just draw you the graph that's in your textbook, just so you know what it looks like.
Is there a bigger number for it?
3 points, no, it's right, there should be. It's right above equation 3.60. I didn't write down the figure number for it, I'm sorry.
Oh, that's okay.
I'll make sure that, does anyone have the textbook? I can find it for you in a minute. Yeah. You have it? Okay, I'll grab it. Oh, now the question is, do you all have the same page number set? I think so. Okay, so. Here we go. Figure 320 on page 88.
320?
Yeah, 320 on page 88. Seemed pretty curious. I didn't think my drawing of it. be able to calculate your field modulus here, okay? And then here's one. And it plots different values for different betas. So you also need to calculate your beta. Remember your beta. Let me make sure I get that right.
Would there ever be a case where we calculated our data and it fell equation lines?
Pardon me?
Do you ever get a case where we calculate our data, it's not exactly one of those lines,
Oh, absolutely.
so you just interpolate?
Yeah. Yeah. So what CC just asked is, you know, obviously this is beta 10, 1.1.01. If you calculate a beta of 4, you're going to have to do a best guess. So it's not perfect. You're still doing a bit of interpolation. So you go, well, this is sort of logarithmic, so it's probably a little bit closer to the 10, so it's probably somewhere along there if it's a 4. So that's a good question. Yeah, you probably won't get that nice thing. So again, let's look at what happens. If we have a really high substrate concentration, then we end up with a really low beta. And what we predicted is that we would have a really high effectiveness factor. So diffusion wouldn't be limiting it. Okay, so what we said is, it doesn't matter how fast it's going super fast. Basically, there's way more substrate than you can possibly need if beta is really low, because the substrate concentration is super high, and that comes across in this graph. You're seeing just that. Now, for beta approaching infinity, which was the opposite case, we had that first order reaction, we actually can calculate your effectiveness factor. Now, only, like, if basically much bigger than 10, you can use that equation instead of reading off the graph, which is kind of handy. But don't use that if it's less than 10 or less. Then you have to use the graph. Okay? And if you have a really low beta, then you can just say your effectiveness factor is essentially 1, and you're good to go. Conceptually, everyone's following. So what you have to do now is, if you want to figure out what your reaction rate is, you're going to need to calculate your effectiveness factor. In order to calculate your effectiveness factor, you need to figure out your field modulus and your beta, and then you go to figure 320, and you figure out what your effectiveness factor is. And always just double checking your brain to make sure that it makes sense. Okay, same thing I said, it was first order reaction rate divided by diffusion rate. So if you have a really high field modulus, that means you have a really low diffusion rate, and it's very diffusion limited. You're getting to lower and lower effectiveness factors, right? The higher your field modulus is, the lower your effectiveness factor, because you're very diffusion limited. Okay. And same thing if you have a very low field modulus, it's because you have a really high diffusion rate compared to your reaction rate. So your reaction rate limited in that case, you're not diffusion rate limited, and you're going to have a really effectiveness factor really close to 1. Okay, makes sense? What do you think would happen to your effectiveness factor if you decreased your particle size? So you can do it mathematically, but decrease particle size.
Effectiveness would go up.
Yeah, your effectiveness factor would go up. Now let's think about why your effectiveness factor would go up. You're decreasing your particle size. Why would it be that you have a lower effectiveness factor closer to 1?
The radius would be smaller, so it would be easier to get to the middle.
Right, so it's the smaller and smaller your particle, the less and less diffusion limited you're going to be. The more and more it's like your enzyme just in solution. So it's sort of going to the infinitely small particle, then that's the same as having your enzyme in solution. So every time it gets bigger, that's adding more diffusion limitation and more diffusion limitation, which is reducing your effectiveness factor. Okay, so again, now let's say we keep the same size of, why wouldn't you just have really, really, really small particles? What would be the things that would limit your particle size? You want as small particles as you can get away with. What might be the practical considerations that would limit your particle size?
Construction of them, I guess.
Yeah, you can't make them really small. You can't, if they're really, really small, you can't filter them out, so they clog up and they jam up the end of your reactor instead of floating around free. And then they're just not as stable and strong when they're really, really small. So they'll agglomerate or behave not just as free-floating particles if they get too small. So there are practical limitations on how small you can make it, but generally in designing particle systems for enzymes, you want them to be as small as you can manage practically. But okay, so we've got this particle that's as small as we can manage practically. We'd really like to increase the enzyme loading so that we don't have to have as many particles floating around our reactor as before. We want to have our reactors be pretty small and not very many particles, so we want to try and put in more enzymes. What's that going to do to our effectiveness factor? You can't just determine it from that, unfortunately. You have to think about it. Well, you can a bit. No, you can't. You have to think about it. This one you have to think about. So we put in more enzyme. Yeah.
Shouldn't it increase or make it closer to 1 because you have more enzyme available to react, so it should be easier for a substrate to find the enzyme?
So let's see, we have.
But there would also be more hindrance too, so I don't know how you
You
figure.
mean what would the more hindrance come from?
Well, I mean, if you're more densely packed, there's not always a chance that an active site would be available. It might be hindered by something else in this way.
So imagining that you could get it there more densely with still the enzyme activity maintained. Think again essentially about, so you're increasing the reaction rate, but your diffusion rate is unchanged. So if you're increasing your reaction rate, you're increasing your Thiel modulus, what happens to your effectiveness factor? It goes down. So the reason that that happens is, say, before you had a few enzymes sprinkled through, you had substrate come in, react, go out, substrate come in, react, go out, and so on for each of them. That happens pretty easily. You've got some diffusion limitations, but generally it'll get into there. Well now, if we pack the enzymes really tightly, we're increasing the reaction rate everywhere, and you've got the same substrate concentration here. Goes in, reacts, comes out, goes in, reacts, comes out, and your reaction rate at the surface, or near the surface, is actually balancing the amount of diffusion that you can get in. So the whole core ends up not being used if you've got too many like your packing of enzymes is too high. So essentially then you're just using the outside, and this whole part, because reaction rate is really high and diffusion rate is really low, you react it all at the, basically near the surface of the particle, and it never gets into the center of the particle. So you're essentially not using the enzymes that are in the center of the particle, and that's what leads to your effectiveness factor getting lower.
How would you decide then how densely you want to pack this? Is there a function where there's an optimal?
So Cece had a really good question. How do you decide at what point you have too much enzyme per particle? You have to do it experimentally.
You just make an empirical model.
Yeah, you just have to do. I mean, there may be some ways. I'm not going to teach you any of those ways in this course, but essentially you want to make sure it's a balance, right? Because that ends up being kind of wasted enzyme if it's not being used in the center. Having said that, still, if you've got relatively small particles and lots of enzymes packed in the center, you still may end up with a smaller total volume of particles needed in total after that. But it's important just to recognize what the influences are of things like particle size, things like your substrate concentration versus Km, how tightly you pack the enzymes in the particles, and so on. Where we're going with this is the same sort of strategy as we had with the surface thing, and we're going to come up with the steps that you need to take in order to, once we put these particles in a reactor, what do you need to do in order to solve the problem of the particles in the reactor? So that's what we're going to do on Wednesday, and that'll give you all the tools that you need to do your assignment.